Hi, this is Dr. Collins Jones. I created this series of videos on Solution Lab Math in the hopes it will be useful to my current and former students, as well as to anyone else who might want an introduction or a refresher to basic lab math. This series of videos will focus on Solution Lab Math, including basic definitions, different ways to express concentration, the preparation of solutions, and how to do dilution calculations. I recognize there are many different approaches to solving these types of calculations. I am presenting the approach that seems to work the best for my students. Please use whatever approach works best for you. I have broken the entire Solution Lab Math presentation into a total of 5 segments. Right? Segment 1, solution vocabulary and concentration units. Segment 2, solution calculations. We're going to focus on how to do concentration calculations. Segment 3, we're going to introduce you to dilutions and dilution factors. In segment 4, we're going to discuss how to prepare multi-component solutions. And in segment 5, we will cover serial dilutions, parallel dilutions, and some common lab dilutions. Let's get started then with segment 1, solution vocabulary and concentration units. Solution vocabulary. A solution, it is a homogeneous mixture of 2 or more components. In order for this to be homogeneous, all of the components must be completely dissolved. There are no particles floating around. It is not cloudy. It is clear. There is no turbidity. It is a clear solution. A homogeneous solution is analytically identical throughout. And what that means is it doesn't matter where in the solution you take a sample and test it, the composition and the concentration will be the same no matter where you take a sample from. Okay? A solution then is composed of a solvent plus 1 or more solutes. All right? The solvent dissolves the solutes, and the solvent is what is present in the greater amount. Okay? In our examples, because we are a biotechnology program, we are going to focus on aqueous solutions. Other solvents, methanol, hexane, whatever, could be used as a solvent. But in the biochemistry lab, in a biotechnology lab, we generally use aqueous solutions. And an aqueous solution is a solution in which water is the solvent. And when we prepare aqueous solutions, we use type 1 ultra-pure water to prepare our solutions, right? And type 1 water has a resistivity of 18.2 megaohms, because essentially all of the ionic substances have been removed. There's nothing there to easily conduct electricity, so this water has a very high resistance to conducting electricity, and it has less than 10 parts per million, ppm is parts per million, total organic carbon. So TOC is total organic carbon. So total organic carbon contaminates water. It could be dead bacteria, it could be dead plant material, it could be pollution such as gas or oil that people poured into the water system. And so any of those components could interfere with what we are trying to do in the lab. So we want to remove the total organic carbon, and that is done with a filter that contains activated charcoal. That is charcoal that is really ground up and has a lot of surface area. And the charcoal will absorb a lot of the organic material. It will stick to the charcoal and it won't come out at the end of the water purification system. All right? So we use ultra-pure water. The solute is what is dissolved in the solvent. Okay, and a lot of times people focus on a single component, and so examples of a solute could be things like sodium chloride, it could be glucose, it could be ATP, it could be a buffer like tris or heaps or phosphate, but that would be a solute. It is dissolved in the solvent, and when it dissolves, it disperses uniformly throughout the entire volume so that it is homogeneously dispersed. It's everywhere in the solution. Okay? In a multi-component solution, which is really common out in the real world, a multi-component solution contains 2 or more solutes. So multiple solutes are dissolved together in the same solution, but probably in differing amounts. And again, they're homogeneously dispersed throughout the solution. And so, we can put in lots of components. Sometimes we make a multi-component solution that contains as many as 5 or more different solutes, and they all must dissolve completely, and they must be analytically identical throughout the solution. One of the limiting factors here is the solubility of each component in the solution and the maximum capacity of the solvent to dissolve all of those solutes together. That is, you can only put so much solute into the solution before it becomes saturated, and there's no more possibility of dissolving any additional solutes. Okay, let's just then quickly review the units of concentrations, and in the upcoming segments we'll actually use these units, these definitions, in calculations. So concentrations tell us how much solute is dissolved in a specified volume of solvent, often referred to as a unit volume. So the specified volume is a unit volume, and that unit volume is usually begins with a 1. So 1.0 liters, 100 milliliters, or 1.0 milliliters. The common units of concentration are molarity. Molarity is denoted by a capital M. And as you record things in your lab notebook, as you record things on batch records, it is really important to pay attention to whether the recorded letter should be uppercase or lowercase. So pay attention to upper and lowercase. Molarity is uppercase or capital M, and it is defined as the number of moles per liter. And remember, 1 mole is 6.022 times 10 to the 23rd atoms, ionic compounds, or molecules, right? And really 1 mole is 6.022 times 10 to the 23rd of anything. Could be 6.022 times 10 to the 23rd pennies. Could be 6.022 times 10 to the 23rd elephants. But here we're dealing with chemistry, biochemistry, biotechnology, so we're going to stick to atoms and molecules. Percent weight volume is the grams of solute per 100 mils of solution. The grams of solute per 100 mils of solution. Percent volume is the milliliters of solute per 100 mils of solution. So weight volume deals with solid solutes, right? The solute is a solid, a powder or crystal or whatever. And percent volume deals with solutes that are liquid. So that would be something like dissolving methanol or isopropanol or ethanol into water. So those all come as liquids. So we would want to record this as a percent volume. And then sometimes it's just easier to express things as a mass per volume. And this could be any combination of units. This could be milligrams per mil, milligrams per liter, micrograms per milliliter, micrograms per microliter, any combination of mass per volume. It is important to note, however, that concentration is based on volume, and volume can depend on the temperature and pressure, right? If you heat up an aqueous solution, the water begins to expand, right? There's more space between the water molecules because of the heat energy, and so the volume increases. It may not be huge depending on how much you heat it, but the volume can change depending on the temperature and on the pressure. So oftentimes, volumetric glassware, that is glassware that is designed to hold a specific volume of liquid, like a 50 milliliter volumetric flask, a 100 mil volumetric flask, a 250 mil volumetric flask, and so on, they are designated as either TC with the temperature, in this case 20 degrees, and the TC stands for to contain at 20 degrees. Or they could be TD, which is to deliver at 20 degrees C. And to deliver means that when you pour it out, this vessel is designed to pour out, say, 100 mils. And even if there's a drop left behind, the vessel has been designed with the people who made that, knowing that that drop will be left behind, but what we have poured out is exactly 100 mils. There's more detail on this in the unit that I am recording on measurement, significant figures, and basic data analysis. So those will also be available on YouTube, and we'll discuss this in a little more detail. But for right now, we really just want to focus on concentrations, and we're going to ignore the often minimal effect of temperature on volume. So our example here is a molarity example. Okay, and so we're going to start with our unit volume, 1 liter. Okay, and in that 1 liter, we're going to dissolve 6 moles of solute. And I'm not specifying what the solute is, I just want to get the concept down here. So we have 6 moles. Each little diamond here represents 1 mole. Remember, 6.022 times 10 to the 23rd molecules here for each of these diamonds in 1 liter. And so moles per liter, this gives us a concentration of 6.0 molar, right? To get a different concentration, there are 2 ways that we could do this. We could increase the number of moles of solute. So in this case, we put in 12 moles of solute in the same 1 liter unit volume, and so our concentration is 12.0 molar. Or we could put the same number of moles, but in a smaller volume, in this case, 1/2 of a liter or 0.5 liters. And so now we have 6 moles in 0.5 liters, or 6 moles divided by 0.5, and we still come up with 12.0 molar, and both of these are now twice the concentration of the original solution. So just trying to get you the concept that concentration depends on the number of moles or the number of grams dissolved in a specific volume. And we're just dividing the solute by the volume, essentially. Okay, some companies use composition for solution preparation. And the reason for this is that composition is based on mass, and mass is independent of the temperature or pressure. So instead of presenting this as a concentration, we present it as a composition. We present this as a composition where the mass of the solute is divided by the mass of the solvent or the mass of the solution. So this is a little more complex, and often in research labs and teaching labs, we just stick with concentrations, and a lot of times even the companies also stick with concentrations. But I just wanted you to be aware that in some cases, composition is the choice for expressing the amount of solute per amount of solvent. And one, if you've taken Introduction to Chemistry, one of these units is molality. So composition expression is molality, where we have the moles of solute divided by the kilograms of solvent. Okay. To wrap up this segment, I just want to give you a few more basic definitions related to solutions. So the first is a standard solution. A standard solution is a solution whose concentration and composition is known exactly. So we have taken great care to prepare this solution. We have weighed things out, usually with an analytical balance, to get lots of significant figures. We know the composition of the solute, so we actually know how pure it is, right? So oftentimes, if you look on the bottle of a chemical, it will give you the purity information on the side of the label. So you might get sodium chloride, and it says it's 95% pure. So if you weigh out 1 gram of 95% pure sodium chloride, actually it's 1 gram times 0.95. And so really what you're weighing out is 0.95 grams of sodium chloride, and the other 0.05 grams are the impurities. And so when we make a standard solution, we take all of that into account when we weigh out the solute. Okay? Standard solutions are often used in the determination of the concentration of an unknown solution. And most commonly, we use standard solutions in biochemistry and biotech to prepare a standard curve. And so in a standard curve, we prepare a series on several different standard solutions at known concentrations, right? So we're changing the concentration of the standard solution, And then we measure some property of each of those different concentrations. Oftentimes, we're measuring the absorbance using a spectrophotometer. But there are other things that we can measure, the change in pH, temperature, whatever. But usually, it's a spectrophotometric measurement. And so remember that what we are changing, right, which in this case is the concentration of the standard solution, what you change, you plot on the x-axis, and what you measure or read, you plot on the y-axis. And oftentimes we design our standard curve so that it is a straight line. It is a straight line. Because remember, the slope of a straight line is constant. Now you're understanding why you took algebra, right? The slope of a straight line is constant, and we can use that y equals mx plus b equation to calculate the concentration of an unknown quite accurately by rearranging that equation. And again, I will have how to deal with standard curves, especially for protein assays, in an upcoming segment. But the types of analysis that we can do are analyte determination, which is an analyte is just a molecule or family of molecules that we're trying to measure in solution. So this could be a glucose determination, an ammonia determination, a lactic acid determination. We use standard curves for protein assays, oftentimes for enzyme assays, for ELISAs, which are an immunoassay, and for qPCR, which is an assay to determine how much RNA or DNA is present. Okay. Now, moving to sort of a different concept is the idea of a stock solution, right? So stock solutions often are not standard solutions, but they're commonly used solutions for things like electrophoresis or other kinds of buffers. And so a stock solution is a solution that has been prepared at a higher concentration than it will be used at, okay? And then we need to dilute it prior to use. All right, and so from the stock solution, after we dilute it, we can prepare many working solutions. So the advantage of a stock solution is the idea that we only have to make this one solution, especially if it's multiple components. We may make the stock solution 10 times, right? That's what the 10x means, 10 times more concentrated than we actually would use it. Right? So the working solution is the solution we actually use, and that's often 1x. And so if we make a 10x solution, we can make 10 working solutions from that 10x stock solution. And so the advantage is if this solution contains 5 components, we just weigh 5 components out at 10 times more than they would be in the 1x solution, dissolve that all in the stock solution, and we only have to do that once. And now we can make 10 working solutions by just one simple manipulation, that is pouring out a known amount of the stock solution and diluting it to 1x. So the advantage is stock solutions take up less space in the lab, right? It makes the preparation of the working solution faster if, and this is an important if we make the stock solution correctly and we prepare the working solution identically each time, then our continuity, that is getting exactly the same working solution, increases because we're not weighing out 5 different things. We're just making one measurement each time. The disadvantage of the stock solution is that if you make it incorrectly, if you don't put in one or more components at the proper concentration, or if the stock solution becomes contaminated, then every working solution is incorrect. So, you periodically, if you make a stock solution, you usually put an expiration date on it, and you check to make sure that it's not cross-contaminated, and you store it where it won't deteriorate. So stock solutions are prepared at a high concentration, and they are diluted to make working solutions. And we'll go again through some of these calculations in the upcoming solution lab math segments. Okay? All right. And so that is the end of segment 1.